All right, so you know that you can write trigonometric functions, and you know that you can write inverse trigonometric functions as well. What we're now going to talk about is a brief introduction to deriving and anti-deriving, deriving and integrating inverse trigonometric functions. For example, if I were to say f of x equals the inverse tangent of x, find f prime of x. First thing, don't mix it up with tangent. Do not say, don't get confused and say, oh, they're saying that f of x equals tangent x, so f prime of x equals secant squared x. No, don't say that. That's not what they're asking. The inverse tangent is different. Again, it's a brief introduction, so I'm not going to go into too much detail on it. But first step, don't mix up the inverse trig with the original. Second step, let's change the notation a bit. We could do this with the f function notation, and we could pull out the limit definition of the derivative and do a long proof. But tangent in particular lends itself to a simpler demonstration of what's actually going on. First thing, I'm going to rewrite it. I'm going to write it as y equals inverse tangent of x. The y notation will be a little simpler here. Secondly, I'm going to rearrange this function without changing anything. I'm going to write x equals tangent of y. That's what inverting a function means, to swap out the dependent and independent variables, to switch the two things you're talking about. Except I haven't really switched them here, I've just rearranged it. Okay, so these two statements are identical. They're not inverses of each other, they are identical. They're the same statement. There is a difference that we're going to not get into right now in terms of the principal values of tangent. Remember, as you should have learned in pre-calculus, the domain and range of inverse tangent doesn't switch with the domain and range of tangent. Okay? That won't be important for what we're doing today, but inverse tangent is one of those artificially restricted functions. It wouldn't normally be a function, but good news, we're going to completely ignore that. We are going to think a minute about what this actually says. We're going to go back, ignore everything about functions, inverse functions. We're going to go back to triangles, specifically right triangle trigonometry. What this statement would have said to you in your original geometry course somewhere is that there is an angle, and that angle is labeled y. And the tangent of that angle, remember tangent originally opposite over adjacent, that hasn't changed. Nothing you've done since with tangent functions, with tangent lines to a curve in calculus, hasn't changed the trigonometric relationship between what you're taking the tangent of, an angle, and a ratio. So for the tangent of y to equal x, then the ratio of opposite to adjacent of our triangle, where y is the angle, we're finding the tangent of y, well, this triangle must have an opposite side of x and an adjacent side of 1. It's got to be the ratio of x to 1 in this case. That's what this statement literally means. The tangent of y, the tangent of an angle called y, equals x. Ratio of opposite to adjacent must be x to 1. Well, that's two sides of our triangle. I'm going to go ahead and find the hypotenuse of this triangle now. I'm going to use the Pythagorean theorem. A squared plus b squared equals c squared. Here means 1 squared plus x squared equals c squared. That means c must be the square root of 1 plus x squared. Okay, so here's everything we know about a triangle somewhere in the world where the tangent of an angle called y is equal to x. That's really all we need to know. Now I'm going to do something a little bit different with this statement. I'm going to go back to my x equals tangent y statement, and I'm going to use some implicit differentiation here. That means derive everything as you go and follow the chain rule. For example, the derivative of x would be dx. The derivative of tangent would be secant squared of y. Inside function never changes. And then we put a dy on the end. And now we're going to solve this for dy over dx. So let's see. Divide both sides by secant squared of y, and divide both sides by dx. And what we get is dy over dx equals 1 over secant squared of y, which I'm going to write as cosine squared y. Okay, our goal was to derive an inverse trigonometric function, and we've done that. We started with a function, inverse tangent of x. Its derivative is cosine squared y. It's a little weird though. Usually when you take a derivative of y, when you have a function of x, dy over dx usually equals something with x's in it. Let's see what we can do about that. All right, going back to our triangle here. If we look at our original triangle here, where y was the angle and tangent was x over 1, well, the cosine of this angle y would be adjacent over hypotenuse. So that would be 1 over the square root of 1 plus x squared. So cosine squared of y would be 1 squared, which is just 1, over my denominator squared, which just means the radical will disappear, and we'll have 1 plus x squared. These two things are identical. So that tells me that if I want to write dy over dx in terms of x, it's going to be 1 over 1 plus x squared. So by drawing a triangle and pretending we're back in our original geometry course, we can take something that would be very difficult to prove with the limit definition of the derivative, and with some clever substitutions and just following everything you learned back when you were first introduced to sine, cosine, and tangent, we can prove that if you start with your function being the inverse tangent of x, it can be rewritten as x equals tangent y, implicitly derived, substitute back in from our original triangle relationship, and the derivative is going to be 1 plus x squared. To write this a little bit more neatly, the derivative of inverse tangent of x is 1 over 1 plus x squared. Chain rule applies. Have to follow the chain rule for this. So what do I mean by that? Well, let's say, for example, can't pick the color I like. Okay, let's say, for example, it's f of x equals inverse tangent of x squared plus 1. F prime of x then is, we follow the chain rule. Take the derivative of the outside function, which is inverse tangent. So that's 1 over 1 plus x squared, except here we have an inside function. The inside function doesn't change. If the derivative of the inverse tangent of x is 1 over 1 plus x squared, well, we don't have an x in here now, we have an x squared plus 1, so that goes where the x did in our formula. We derive inverse tangent 1 over 1 plus something squared. What is that something? X squared plus 1. We didn't change the inside function between here and here because We don't take the derivative of the inside function until after we've taken the derivative of the outside function. Chain rule says multiply by the derivative of our inside function, which is x squared plus 1. Derivative of that is just 2x. So your final answer might look something like 2x over 1 plus x squared plus 1 squared. Or if you're looking for it among multiple choice alternatives, it might be 2x over, if we FOIL this, we will get x to the 4th plus 2x squared. We would normally get plus 1, but instead here we're going to get plus 2. X to the 4th plus 2x squared plus 1 from FOILing our inside function squared. Plus 1 more gets me the plus 2. This would be my final answer. Another quick example of this, shorter one. If we have y equals inverse tangent of, say, e to the x, well then our dy over dx or y prime, again, follow the formula like you have with other derivatives. It's going to be 1 over 1 plus whatever our inside function is squared times the derivative of our inside function, well, the derivative of e to the x, I mean to put that mark there, is just e to the x. So your final answer might look something like, won't look like that probably, might look something like e to the x over 1 plus e to the x squared. More likely, they will apply the middle school rule of a power raised to a power. Is a case where you multiply the exponents, and that is 1 plus e to the 2x. It can be challenging sometimes to see this in an integral and to have to figure out the chain rule substitution. I'll do an example of that in a moment. But first, let me just write this rule and two others a little bit more simply. These examples, okay, I'm going to do away with those. They're still on the last page for those of you who have access to the PDF. They're not gone forever. And now, there are two other inverse trigonometric ones I'm going to just mention today, and I'm not going to prove where they come from. It can be done, but I don't think it's the best use of our time. And they are that if you have the derivative of inverse sine of x, that is, and I just want to make sure I write it correctly. This book uses slightly different notation. Okay, that will be 1 over the square root of 1 minus x squared. And the derivative of inverse secant of x is the other one I just want to mention, because that will be your 1 over the absolute value of x, square root of x squared minus 1. These two can be very easy to mix up. They can be very easy to mix up, which is why I kept double checking them. Okay, these are the three differentiation rules you'll have to know for the AP exam. I'm going to now do some examples of anti-deriving and just show you how these can be reversed. Anti-deriving as usual. If you know the differentiation rule, you have to know it forwards and backwards. And you have to recognize it with inside functions, and those inside functions and their derivative. So let's pull a good example from another source. Here we go. Integration example. Okay, sometimes math is very picky. For example, if I said find the derivative, or the antiderivative rather, of x over the square root, nope, not the example I wanted, my apologies. That's something that's going to come up a little later. Let's say 2 over 4 minus x squared under a square root. Now, the problem with this example is, like I said, math can be very picky sometimes. There are certain things like in conics with ellipses or hyperbolas, or with polar conics. Conics are very picky, where the rules and the tricks we teach you only work if certain numbers are equal to very specific things. For example, this derivative only produces a 1 here. It only works if this is 1. Okay, so we don't have a 1 there. So this apparently can't line up, say, with this one. This inverse sine derivative only produces a 1 there. Which means, see, this one here, what you should, I hope, notice about this antiderivative is it looks so much like the derivative of inverse sine. That 4 is going to mess us up. It has to be a 1. So what can we do about that? Some books and teachers will just give you a formula. I like to go through a process, reinforce some basic skills along the way. Here's what I'm going to do. I'm going to factor a 4 out of both terms. So this becomes 1 minus x squared over 4 inside my radical. Okay, now I've got my 1, but I also have that 4 there, so that's problematic. We'll take care of that in a minute. I hope it's not a shock to you at this point in your mathematical development that if you have two things being multiplied under a radical, you can split them into two different radicals. So let's go back a step. I had 4 minus x squared. I didn't like that. It looked a lot like my this part looked a lot like the derivative of inverse sine, but it wasn't quite. I needed to get that 1 there. So I factored a 4 out of everything. Now I have my 1. Okay, now this is starting to look like my arc sine, inverse sine derivative. That's the whole point of anti-deriving. You try to make it look like the derivative of something. And factored the 4 out. And now, since I just have multiplication between the 4 and the quantity 1 minus x squared over 4, I can split it into two radicals. Square root of 4, I can now evaluate. And I have 2 divided by 2 square root of 1 over x squared over 4 dx. I am so close. In fact, I could just do that. I'll be left with a 1 on top. Close, but still not done yet. So now I'm looking at the integral of 1 over the square root of 1 minus x squared over 4 dx. As soon as this looks like my inverse sine pattern, I'm done. Here's the problem. This is going to be really annoying for some people. I have x squared over 4. I don't have x squared. Not a problem. This is what u substitution was basically invented for. It doesn't really matter whether it's x or u or anything you can imagine being squared under there. The point is something is. And what is actually being squared under my radical is x over 2. X squared over 4 is a fraction with a perfect square in the numerator, a perfect square in the denominator. So what I have here is x over 2, whole thing squared. In other words, my u, my inside function for u substitution, is x over 2. Now the way u substitution works is you have to have an inside function and you have to have its derivative. So well, let's see, the derivative of x over 2 is 1/2 dx. The x goes to 1, dx appears. I don't quite have a 1/2 dx. I'm so close. I would like to have a 1/2 dx. Well, I can do that. I can replace the 1 with a 1/2 as long as I balance it out somewhere. I can put a 2 out in front. 2 times 1/2 is 1, they cancel out. The point is, I have my inside function x over 2 and its derivative. The tricky part about inverse trigonometric functions when you're anti-deriving them is that if you're used to looking for a u and a du when you do your u substitution, here your u is being squared. You have to figure out what's being squared and see if you have that inner function, that innermost function that's being squared. You have to see if you have its derivative or if you can make its derivative appear by manipulating coefficients. Change the 1 to a 1/2, put a 2 on the outside to balance it. Any way you picture it, we now have our antiderivative is now equal to 2 times the antiderivative of 1/2 over the square root of 1 minus x over 2 squared dx. So this in here, the part in the integral, this is the derivative of inverse sine of x over 2. Because this was an indefinite integral, we put a plus c at the end, and this is our answer. I'll do another example or two of these. Okay, so for my next example, clear a little room here. But I want to leave my 3 formulas up because they'll help. This next example, I want to look very much like the last one we did to reinforce the idea behind it and to show you what some of the little issues that can come up with this. Now, we are going to look at the antiderivative of x plus 2 over the square root of 4 minus x squared dx. Okay, first thing, that plus 2 kind of makes a mess of things. The addition on the top. Terms always make things a little bit trickier. And we've already done half of this problem. We know what the solution to half of it is. We wouldn't necessarily have to do that one again. So here's my thought. Let's split this into 2 integrals, one of which we haven't done before, and the other we have. Now this illustrates part of the trickiness behind these inverse trig integrals. They look like a lot of other integrals. These two things look very similar. What you have to be able to recognize here is that you have a much simpler u substitution possibility in this case. If you set u equal to 4 minus x squared, then du is negative 2x dx. Do we have a u-du relationship? We're very close. We have an x dx. We don't have this negative 2. I can put the negative 2 there, and I can just make a little more room for myself over here. And I can put a negative 1/2 out in front of my integral to balance out the negative 2, and now I have an inside function and its derivative. Meaning this first integral can be rewritten as the integral, well, I like to write it as negative 1/2 times the integral of u to the negative 1/2 du. Square root on the bottom is the same thing as negative 1/2. My inside function is inside that radical. That's my u to the negative 1/2. My du is the derivative of my inside function, which includes my negative 2x and my dx. This is a straightforward powers rule situation. I'm going to go back to writing it without the u, but with the original notation. Powers rule says add 1 to your exponent, 1/2, negative 1/2 plus 1 is positive 1/2. Inside function doesn't change. My u was 4 minus x squared. And divide the whole thing by your new exponent. I'm not going to redo the second part of the integral, but ignoring it for a while, because we already figured that one out. This one we figured out was the inverse tangent of x over 2 plus c. This isn't quite fully simplified yet. I need to do a little bit more, but I ran out of room, so let's see if I can give myself just a little bit more space here. And now I can cross out those 1/2, make sure I remember that the negative is still there. And my answer should look something like, this is negative square root 4 minus x squared plus the inverse tangent of x over 2 plus c. So, oh, I missed something. We had a 2 here in the front of our second integral. I knew I was forgetting something. So we split this up. We had this original problem that didn't work as a u substitution and didn't work as an inverse tangent. Couldn't reverse any of these derivatives to get back to an inverse function. But if we split it into 2 fractions, we get a u substitution of a type we've done before and an inverse trig. An inverse trig integration. So, and again, I can't stress enough, these 2 integrals look very similar but are solved very, very differently. Let's do another example. I'll throw another u substitution trick at you for this one. This one is going to be the integral of, I'm going to make sure I get it correctly, dx over the square root of e to the 2x minus 1. Okay, a couple of problems right away with this one. E to the 2x, first of all, is something squared. So when you see something squared in a construction like this under a radical, inverse trig should come to your mind. But you got to be careful on the details. The details are important. This has to equal 1, check. Okay, it looks very much like the inverse sine problem, but it's not. Because for this one, we have a problem. If my innermost function, remember, u in this case will not be e to the 2x minus 1. It's not everything under the radical in the case of integrating to try and get back to an inverse trigonometric function. U, your inside function, will be whatever's being squared under the radical. So that would just be e to the x. Well, du, derivative of e to the x, is e to the x. Chain rule tells me to put a dx there at the end. Okay? I don't have another e to the x being multiplied by dx anywhere. Looks like we're stumped. Except, hopefully you've seen at this point that differentials, the du and the dx, differentials can be manipulated like other variables or prime numbers. For example, what if I chose to solve this for dx? Dx would then equal e to the x over whoops, let's write that backwards, would then equal du over e to the x. Okay, well now this doesn't help us much. We can't have a mix of u's and x's here. If I put du over e to the x in here, this integral would be a mess. I mean, here, I'll actually show you. If I follow this u substitution as I've written it, I'll move over here a little bit. If I start subbing in for u's, the bottom's no problem. I will get the square root of u squared minus 1. Okay, that's all good. It's similar to my sine. It's also similar to my inverse secant. But on the top, I will have du divided by e to the x. Well, we can't mix x's and u's in our integral. It's got to be all one variable. We need to have a du. If we have a du in there, everything else has to be u. The e gives us a rare opportunity, though. U was equal to e to the x. So wait a minute, I can take this e to the x and substitute it in, switch it out. If e to the x and u are the same thing, then this integral becomes du over u divided by u squared minus 1, which can be rewritten as du on the top. Dividing by something in the numerator is really the same as multiplying by something in the denominator. Oh, this now looks very, very close to our inverse secant derivative. This is so close to our inverse secant derivative. The only thing missing is the absolute value. Well, absolute value, distance from the origin, as an operator means make whatever's inside positive. U is equal to e to the x. E to the x is always positive. I don't have to worry about that. That allows me to go ahead and say that what I'm looking at is the inverse secant of u plus c. Not the inverse secant of u squared, or u squared minus 1, just of u. And what did u stand for? This problem didn't start with the letter u. U was representing e to the x the whole time. So that's another u substitution trick. These are some of the more difficult integrals. And we will spend more time on them in the future in class, as I hope you will in whatever other classes you may be taking, but this is another example of how they play out. Needless to say, this is another case where you're really not allowed to forget anything you've ever learned in any prior class, unfortunately. For example, I'll do one more example of these. All right, for this example, we're going to start with an integral that is not going to look particularly helpful. I'm definitely not making this example up. Okay. Make sure I've written that one correctly. Okay, common example. This integral doesn't look like anything good. It's similar to some patterns we've seen. It can't be du over u, so it can't antiderive to a natural logarithm. There's no u or du in there, apparently. This one just doesn't look like anything we've ever seen before, or that we can easily do. In fact, before this lesson, the correct answer is I cannot set up a chain rule, so I can't do it. I can numerically approximate it with trapezoids or my calculator, but if it were a definite integral, but I can't do this. Okay, here's a big trick you can use. We're going to go back and review for a second, completing the square. Completing the square is where you ask yourself a certain question. And that question is, how can I take a polynomial that is not a perfect square and force it to sort of be one, make it look like one? So we're looking at x squared minus 4x plus 7. And what we would like to do is put a number here in between the minus 4x and the 7 that completes the square. What does that mean? Well, completing the square means following this pattern. Since we have a negative sign here, it means we're looking to follow the pattern a minus b squared equals a squared minus 2ab plus b squared. In other words, can we create a trinomial that looks like a squared minus 2ab plus b squared? Because if we can rewrite it as a minus b squared. There's a little bit of a pattern here. This minus 2a, I'm going to write this one other way, so hopefully it'll be a little more clear. If I had x minus some number squared, that would work out to x squared minus n times x minus another n times x, so minus 2n times x. My last term would be plus n squared. I'm going to pick a number that will fit this pattern here for what we were given. So we get a 2n here and a minus n here. Okay, the minus 4. If I were looking at this trinomial first and trying to get back here, this number would be half of this middle coefficient. And the number I would want at the end would be half the middle coefficient, half of 2n squared. Cut 4 in half, you get 2. Square 2, you get plus 4. I hope that wasn't too confusing for people who haven't seen completing the square before. It was just a quick review of it. But what this basically means is, if I can put a plus 4 here, then I can rewrite this in a very helpful way. But I can't just put a plus 4 here. It has to be equal to what we started with. So if I'm going to put a plus 4 here, I also have to put a minus 4 at the end. Whatever we do here must be equal to whatever we started with. So if I'm going to put this plus 4 here, I have to put a minus 4 back here. The advantage to this is now, instead of x squared minus 4x plus 7, I can now write that as x squared minus 4x plus 4, put that in parentheses, plus 7 minus 4. All I've done is added a 4 and taken a 4 away. They cancel out. I'm allowed. But now I can rewrite this part. This is now my perfect square trinomial. If you cut the middle coefficient in half and square it, put that in there, you always get something that can be reduced to a binomial squared. Multiply x minus 2 times x minus 2, you will get x squared minus 4x plus 4. Plus 7 minus 4 is plus 3. It's a bit of a long way of saying I can rewrite my integral as the integral of x minus 2 squared plus 3. Why did I do that? Look over here at the derivative of inverse tangent. The derivative of inverse tangent is 1 over 1 plus x squared. We're close. We have dx over something squared plus 3. This 3 again is a problem. See, if we could get this something squared plus 1, we might have an inverse tangent situation. So let's see what we can do with that. I'm going to rewrite this a little bit. I'd like a 1 on top. I'll move the dx over to the end, no problem with that. I'm going to factor 3 out of everything on the bottom. X minus 2 squared, factor 3 out, just winds up being x minus 2 squared over 3. And now it's plus 1, because I factored the 3 out of the 1. I can keep factoring this 3 out of my denominator and write it as 1/3 out in front of the integral. And now I have 1 over, switch these two terms around, 1 plus this fraction, x minus 2 squared over 3 dx. It's not the prettiest integral in the world, but it will work. I'm looking for 1 plus x squared. Well, I'm going to use u instead. And I'm going to say that u squared is x minus 2 squared over 3. So u, take the square root of the numerator, x minus 2 squared becomes x minus 2, square root of the denominator, square root of 3 is just the square root of 3. I'm not going to rationalize it right now. And now then, what's du in this case? Let me write this out a little more. This is x over the square root of 3 minus 2 over the square root of 3. So du, this is just 1 over root 3 dx. Treat the 1 over root 3 like it's a coefficient, and the derivative of any coefficient times x is just that coefficient times dx. Minus 2 over root 3 is a constant, so that goes away. So we almost have our integral. I think I'm going to need another page to do this a little bit more clearly. Don't worry, this isn't gone forever. And I'll go from that step to get rid of the completing square examples. And move that up there a little bit. Okay, now I have enough room to finish. And I'm looking at, okay, du is 1 over root 3 dx. Going back up to, I lost part of my original integral, didn't I? Let's put that back in there. I lost the 1 over. Okay, go back to my original integral. I don't have a 1 over root 3 dx. I have a 1 on top. So I need to put a 1 over root 3 up here. And I can balance that by putting a root 3 out here. So I'm almost ready to integrate. I will have root 3 over 3 at the beginning, then my integral sign, 1 over root 3 dx over 1 plus u squared. I want to write this as x minus 2 over root 3, whole thing squared. Ignoring the coefficient out of the front, I now have 1 plus u squared, and I have the derivative of u on top. My answer is root 3 over 3 inverse tangent of just my innermost function, not squared, x minus 2 over root 3 plus c. This is probably a little bit more involved than I'll ask you for, definitely on a multiple choice section of the AP Calc exam, at least. But if you can get your head around this, you can handle pretty much anything they throw at you. Anyway, those are some examples of inverse trigonometric functions being derived and anti-derived.